Hi, so in this video, we're going to talk about DOPA decarboxylase or DDC. We will be presenting information to you through drawings, arrows, and keywords. And Luis Chavez and myself, Andrea Peña, will be presenting this information. So we will be talking about Parkinson's disease and the role of DDC. The mechanism, we'll go ahead and explain that. Also the drug and inhibitors that are used and other information. Starting off, we'll talk about Parkinson's disease. So this is thought to be caused by the deficiency of dopamine in the brain due to the deterioration of dopamine producing cells. In this case, dopamine rich areas, for example, like I'm drawing here, is the substantia nigra. Now, dopamine is a neurotransmitter that gets released by neurons. And when we have Parkinson's disease, dopamine doesn't get released nearly as much as it's supposed to. So the vesicles containing dopamine are affected, and we end up releasing a lot less dopamine that our body is actually meant to. So the decreased levels of dopamine in our central nervous system is what then leads to the common symptoms of Parkinson's disease, which are tremors, bradykinesia, rigidity, and postural instability. And again, this happens mainly due to neuron degeneration. Now you may ask, what is the level of DOPA decarboxylase or DDC in Parkinson's disease? And well, DDC converts L-DOPA into dopamine in the blood, and it also transforms L5-hydroxytryptophan into serotonin. Also another fancy word for L-DOPA, it's levodopa or L3,4-dihydroxyphenylalanine. So these get decarboxylated and transformed into dopamine or serotonin respectively. Although DDC is able to convert L-DOPA into dopamine, dopamine cannot cross the blood-brain barrier, which is found in our central nervous system, which is why we actually need the administration of L-DOPA. So L-DOPA is a prodrug where that essentially means that it's administered in its non-active form, and it is then transformed in the body into its active form. In this case, the active form would be dopamine, and it would be transformed in the brain once it's inside the brain. Now, looking at the mechanism of DDC, the conversion of L-DOPA into dopamine is actually catalyzed by vitamin B6 dependent enzyme aromatic amino acid decarboxylase, which is what Bidwin's saying, DDC. So the way in which this happens is that L-DOPA first has to react with vitamin B. Now here we are going to try to explain the mechanism of this enzyme and draw it. Hopefully you're able to follow along. So like I said, L-DOPA and vitamin C have to come together essentially, and this happens through a reaction called condensation, where a water molecule gets released, and also there's a formation of a bond between the nitrogen and a carbon. So once this happens, this is when the decarboxylation can actually happen, and DDC catalyzes it. So there is transfer of electrons, which leads to eventually the carboxylic group getting released from the now formed compound. Also, with the decarboxylation, we now have a release of carbon dioxide and a hydrogen atom. Now, this forms an unstable charge at the top, which, again, shifting of electrons has to happen. So protonation will happen in order to make a double bond between the carbon and the nitrogen, and then the double bond that is formed between the nitrogen and the carbon will eventually break. This will cause the formation of an extra hydrogen bond attached to the carbon. Now that this has happened, a tautomerization will happen, or a proton transfer. So essentially the hydrogen attached to the carbon will move up to the top, and then that will cause the double bond between the carbon and the nitrogen to break. That will leave us with the following structure. And now a hydrolysis has to happen. So a water molecule will attack the double bond, which will essentially cause the separation of these two compounds, and we will finally get the formation of vitamin B6 and dopamine. Now we will move on into talking about the drug and the inhibitor, which in this case is externally supplemented levodopa or L-DOPA and carbidopa, which is the anti-Parkinson's drug. But why combine the two together? Why not just have levodopa, or why not just have carbidopa alone? Well, the thing is that these alone are not effective. They're very ineffective, and they actually have to function together in order to be able to be a viable treatment. So when levodopa is given as an external supplement, it gets synthesized into dopamine in a very fast way. So due to the significant metabolism, the amounts that we actually need for levodopa to be converted into dopamine are not reached into the brain. This is called peripheral conversion, where the majority is actually synthesized in the GI tract or the blood vessels. So this leads to reduced amount of levodopa and dopamine essentially into the brain. So this is when carbidopa is given in order to prevent the peripheral conversion. This here is the structure of carbidopa, which, like I already mentioned, by itself is going to be ineffective. It has to be in conjunction with levodopa. So these two together will inhibit DDC in the GI tract, and so this will cause levodopa or L-DOPA to actually be able to reach the brain. Again, this is a prodrug, so it will reach the brain in its non-active form, and once it's inside the brain, it will get synthesized into dopamine. So with increased amounts of L-DOPA reaching the brain, we will have increased levels of dopamine in the brain. This will also cause a reduction in the side effects that are caused by L-DOPA, and will also reduce the amount of dose that is needed.
Okay, we already talked about the role of the enzyme, the mechanism, and the drugs and inhibitors. The next part, we'll talk about the history of the drugs and inhibitors and see how it has been modified and improved over the years. It's been the same drug for the past 50 years and is the same drug that's being used today. So the dates on the timelines were provided by a journal review in the European Neurology Journal by Robert Hauser called Levodopa Past, Present, and Future. In 1961, DOPA was reportedly used on Parkinson's disease patients intravenously. From 1961 to 1967, you can see that many patients develop motor fluctuations and dyskinesia, which motor fluctuation is the decline in the usual benefit from a dose of levodopa, and dyskinesia is just abnormal movements from the body. In 1967, levodopa activity was enhanced with DDC inhibitors. The first DDC inhibitor was benzorozide, and much improvement was seen from 1961 to 1967 in Parkinson's disease patients. Only 1% of an orally administered dose of levodopa without any DDC inhibitors actually made it to the brain, while 5 to 10% of an oral dose of levodopa administered with a DDC inhibitor was able to reach the brain. The next date that we have is 1969, which combined levodopa and DDC inhibitors proved to be more effective than levodopa alone. The reason was DDC inhibitors did not cross blood-brain barrier, so they were inhibiting DDC carboxylation in the blood and allowing levodopa to reach the brain and be able to be converted into dopamine in the brain, which caused better results for Parkinson's disease patients. In 1974 was the first time clinical use of this combination of carbidopa and levodopa was used, and in 1975, Cymet, the drug for the combination of carbidopa and levodopa, was commercialized, as well as Matopar, which is a different DDC inhibitor combined with levodopa. This was the first combined carbidopa levodopa drug to be commercialized, and was later improved in 1989, which was called assignment controlled release, which showed to further prolong half-life of levodopa. This helped in stabilizing serum levels and decreasing motor complications in these patients. And in 1991, assignment controlled release was commercialized in the US. Research did not stop there, though. Research showed that inhibition of DDC only shifted the metabolism of levodopa to the catechol O-methyl transferase metabolic pathway. So the levodopa, most of it was being still processed in the blood, just by a different metabolic pathway. So in 1998 and 1999, two inhibitors of COMT, catechol O-methyl transferase, were released in order to improve more levodopa reaching the brain to be converted there for dopamine. These enzymes are called tolcapone, which was released in 1998, and entacapone, which was released in 1999. The most recent drug that has been released for Parkinson's disease is a combination of carbidopa, levodopa, and entacapone tablet called Stalevo, which became commercially available in 2003 and is the most recent drug to this date. And more studies are being done each and every day to figure out better ways to improve dopamine levels in the brain, and with decreasing of symptoms and improved motor skills in Parkinson's disease patients.